Hello, welcome back to the next in the series of videos on microprocessors. Today, we're going to understand a little bit about keyboards and displays, some of the basics. In the next video, we're going to understand how to actually interface a keyboard using the 8279. For this video, what are keys? What are keyboards? All of us, of course, have used keyboards along with our computers. But have you ever wondered what happens on the inside? How does a key work? How does that switch work when you press it? How is that switch ultimately recognized by the computer as the letter A, letter B, etc.? That's what I'm going to help you understand. Before that, we need to understand a concept called debouncing. What does this mean? So what's a bounce? What's a key bounce? So if, for example, if you were to drop a ball, a rubber ball onto the floor, it bounces many times before it comes to a stationary position. Right? So just drop it like this, it would bounce and then come to a standstill. Unfortunately for us, the same thing happens inside a mechanical switch. So whether it's your switch in the house, your light switch, whether it is a switch on your computer keyboard, whether it is a switch for your remote control of a vehicle, every mechanical switch has something called a bounce. And what is this? So when two switch contacts touch, you would like them to touch and remain stationary. What in effect happens is they touch, leave, touch, leave, touch, leave, touch, leave, till it finally mates. Now, for us as engineers, this is a problem. Because the moment the switch touches, we think a contact has been made, but the switch is still busy. And we have to wait for this to die down. Let me explain this using a waveform. So this is an example of a switch. And when the switch is at logic high, so this is before the switch is pressed, the input port is pulled to logic high using the resistor. The waveform is at 5 volts. As soon as you press the switch, the waveform drops to 0 volts. When you release the switch, it comes back to 5 volts. And this is a case where the switch closes and remains closed. Unfortunately, this is the ideal world and doesn't happen in real life. Then you say, hey, you know what? You told us about rise time and fall time. Maybe that is more realistic. And indeed, you are right. This is a more realistic depiction of the scenario where you have a fall time whenever the switch is closed and a rise time when the switch is opened again for the signal to drop from 5 volts to 0 and to rise from 0 volts to 5 volts. Unfortunately, this is not realistic enough because remember, the switch in reality bounces. It makes and breaks a contact. So when it is dropping from 5 volts to 0 volts, you will see the signal go up and down many times. Typically, this lasts under 10 milliseconds. But for a processor, 10 milliseconds is a long period of time. Similarly, when the switch is opened, it goes back from 0 volts to 5 volts again in many steps, typically 10 milliseconds. So this signal is much more realistic. And yet, it is still not sufficiently realistic because in this case too, you need the rise time and the fall time for each bounce. The problem with this is that if you were to measure the switch during the high time of the bounce, you would read it as open. Whereas if you were to measure it during the low time of the bounce, you would read it as closed. And this is an error that you cannot afford because when the user presses the key on the keyboard, he presses it once and expects to see something on the display. You cannot wait for the user to keep the key pressed. It just slows down things too much. How do you manage this? This is the process of debouncing, removing the bounce of the switch. How does this work? Let's take a hardware solution for this, fairly straightforward. You use a couple of latches. So as soon as the switch moves, the latch changes state. The switch is a mechanical device, the latch is an electronic device. So what you have done is taken a mechanical device, used an electrical signal from the mechanical device through an electronic device and converted it to an electronic signal. An electronic signal is clean, it has no bounce. Since it has no bounce, the processor sees a steady signal. The advantage of a hardware solution is in the first transition of the switch, the output changes and remains latched. Therefore, the 10 millisecond delay is irrelevant. The latch operates at the first transition. The disadvantage, of course, is the cost. With every switch, you need a debounce circuit like this. On the other hand, what would you do if it was to be a software solution? Well, it's pretty simple, right? So you know that there is a 10 millisecond duration when the switch is in an ambiguous state, neither open nor close, because of the bouncing operation. So what you do is, as soon as you get the first signal that the switch has changed position from open to close or close to open, you read that, wait for 10 milliseconds and read again. And then you know that you have reached steady state and that it was not because of some noise on the line, electrical noise on the line. Very simple software solution to a debouncing problem. You'll see the flow chart of this all over the place. I mean, very simple, right? So check the first signal, wait for 10 milliseconds, 12 milliseconds, and then read the same signal again. And if it matches, you know that the switch has changed state. Typically, this is how debouncing happens, either through a hardware logic or through a small piece of software code. Let me end by talking to you about LCD displays. Now, all of us know about, I'm not talking about the LCD television, right? That's different. I'm not talking about an LED television. I'm talking about 7-segment LCD displays. We know why it's called a 7-segment display. It has 7 different diodes that together form the numbers and letters that you see on a LCD 7-segment display. How is this interfaced to a processor? So what really happens is the 8255 comes in very handy here. If you remember our last video, we introduced the 8255. The 8255, using just 2 signals from the 8255, you could interface 4, 6, 8 LCD individual segments if you so desire to do so. So based on what is required, the processor outputs to what is called the 74164 serial in parallel out decoder. And this decoder takes a series of bits from the 8255 and feeds it into the data input of the 74164, and the moment it is fed in, it comes out as 7 parallel signals for the 7-segment display. And to do this, remember these 4, because we're trying to save the pins on the 8255, we have connected 4 74164s in cascade. So if you wanted to display something on the leftmost 7-segment display, you had to feed it through all the 4 74164s before it became visible on the first displayed digit. Then you feed the data for the second set of display digits, the third set of display digits, and finally the last set of display digits as depicted here. The reason there are many different ways of doing this. This is a design that permits you to use just 2 pins of the 8255, allowing you freedom to use the rest of the 8255 for whatever version you want. It just means a little more software overhead because you cannot address the individual SIPO decoders. You have to do them through a cascade operation. I hope this gave you a flavor for a little bit more understanding on keyboards, keys, and LCD displays. In our next video, we're going to be talking about very specifically the 8279, which kind of interfaces to the 8086 to connect to keyboards. Till then, thanks for your patience. All the best.